So thank you for attending this session dedicated to Java Loom. What I propose here is to address this topic with a very concrete way from a developer perspective. What does this new concurrency model change when we design, develop, configure, and monitor our Java applications? So I'm Jean-François James. I'm software architect at Worldline. I'm also head of the DevRel team in my company. I've been working with Java for many years. What do we do at Worldline? We build and run payment services. When you pay with your card or your mobile, in-store or online, the process in the background is relatively complex and subject to strong requirements, compliance regulations, auditability, security, availability, latency, scalability. In terms of scalability, Worldline managed more than 28 billion transactions per year. So we are interested in everything related to JVM performance. How many of you have never heard of Java Loom? Okay. How many of you have a good vision of Java Loom? A good understanding? Okay. And how many of you have done some tests? Okay. So let's start. Java Loom is an umbrella project. It is made of 3 features. The main one is called virtual thread, and it has become a stable feature with Java 21, freshly released, which is a long-term supported release. So we can say that virtual threads are production ready. There are 2 complementary features which have been delivered in preview mode. They are not production ready. Structured concurrency, I won't say a lot about that. There is a dedicated session today at 12:35. Basically, it enables to run several tasks on top of virtual thread in an atomic way. Scoped values is an optimization of thread locals. Thread locals and virtual threads are not very good friends, as we will see. So the Java concurrency model has never stopped evolving. The cornerstone, the foundation has been established with Java 1.2 and what we call platform thread, also known as native threads. Why platform thread? Because in this model, each Java thread is a scene wrapper on top of an operating system thread. Several constructions have been added, such as executor, for join pool, and so on. Virtual thread is part of this continuum, but with a much disruptive approach, as we will see. Before diving into the solution, what is the problem? What is the main problem we have with our Java backend applications? Most of them are based on the thread per request model, where each external request, HTTP, gRPC, REST, whatever, is processed end-to-end by a dedicated thread. What happens when the processing needs to call a database or a remote service? The process is blocked. And we end up with multiple blocked processes. Java process, Java thread, and consequently operating thread. And operating threads are expensive resources. They are costly to create, about 1 millisecond, costly to switch between 1 and 10 milliseconds. They need a strong memory footprint, and they are managed in kernel mode. At a given moment, the number of running threads is limited by the number of CPU cores. So clearly, from a runtime perspective, this model is not optimal. A lot of overhead on the JVM and the OS for a poorer efficiency. How can we improve the situation? A first approach is to code reactive. How many of you have already coded reactive with Java? Okay. It's a matter of specialists. With this model, each thread can process multiple requests at a time. So this is very efficient because we just have a few threads, typically the number of CPU core, that never block. Very efficient, but coding reactive is difficult. First, there is no standard. You have to choose a library. RxJava, Mutiny, Reactor, Vertex, whatever. Basically, you have to implement pipelines that react in an asynchronous way to events. An event can be an I/O completion, an exception, a business event, whatever. So the main principle of reactive programming, the two main principles are non-blocking I/O and asynchronous processing. So coding that way is not that easy, especially if you have to deal with complex business logic. In contrast, the thread per request model is based on the good old imperative programming style, sequential, easy to code, to test, and to debug. So we have to choose ease of development with imperative programming or efficient runtime and high scalability with reactive programming. Luckily, Luke is coming with a very appealing proposal. We can code imperative as simple as possible and run reactive as efficient as possible. How is that possible? In fact, a virtual thread is a very lightweight construct. It can be created, blocked, removed at no cost. It has no running capacity. When running, it needs to use a platform thread. Okay? So, with this model, we can keep the thread per request model, more specifically virtual thread per request, while having just a few threads in the background, a few platform threads, a few OS threads, very similar to reactive programming. Inside the JVM, everything is based on an internal class called continuation. A continuation enables to start a task, to suspend it, to restart it with two methods. It has two main methods, run and yield. When an I/O is needed, continuation.yield is called. What happens in the background? The platform thread is unmounted from the virtual thread. The Java heap, the Java stack is saved on the heap. By the way, as you can see, there is a pool, more specifically a fork-join pool of platform threads dedicated to run virtual threads. They are called carrier threads. Later on, when the I/O is completed, continuation run is called somewhere inside the JVM. Then the virtual thread can be restarted, a new carrier is mounted, and the heap is restored from the stack. At this stage, are you totally lost, or is it clear? Virtual threads, platform threads, carrier threads. It's okay? So, there are three main principles from a developer perspective with this mechanism. Three important facts to have in mind. First one, everything is managed by the JVM. As developer, we don't have to care. Continuation is an internal class. It is used by the virtual thread, and we can code imperative as usual, using Jakarta, microprofile, Spring, whatever. This is in contrast with Kotlin coroutine, for instance. Second, the more the processing block, the better, with this principle. In contrast, in-memory computing will never unmount the carrier thread. So that means that for CPU-bound processing, it is better to stick with platform thread. Using virtual thread for CPU-bound processing is counterproductive. As an example, in the JVM, JIT and GC threads remain platform threads. Okay? The third point, and it's not a good news, is that we had pressure on the garbage collector and the memory footprint. Because the stack, the Java stack, which reflects the status of the task, the execution status of the task, is saved and restored from the Java heap. So, virtual threads are supposed to be very lightweight. Let's check that. I propose a basic test, Java SE, no complex framework involved. I have used Java 21, tested it on this macOS, which has 8 CPU cores, using G1, which is the default garbage collector. And to simplify the testing, I have fixed the heap size, the XMX and XMS parameter being equal. So this is a loop, a very basic loop, where we create plenty of virtual thread using the static method thread of virtual. Each virtual thread calls a process method. The code is not illustrated here, but it's very basic. It consists in getting the name of the carrier thread and incrementing a counter. That's it. There is also a mechanism that ensures, a whole mechanism that ensures that all virtual threads are present in the JVM. Okay, for this example, so let's run a simple example. Let's create 1 million virtual threads with a heap of 16 gigabytes. Okay, it's running. Boom, done. It has been done in less than 5 seconds. We have used 3 carrier threads. There are 8 CPU cores on my machine, but only 3 carrier threads have been needed to process 1 million virtual threads. Additionally, you have the counter of calls for each carrier thread. So, I guess you are convinced. Virtual threads are indeed light and fast to create. To give you a comparison, the limit with platform thread on this same machine is around 32,000 platform threads. So 1 million is okay, less than 5 seconds. According to you, what is the maximum possible on this modest laptop? 2 million, 10 millions, 20? Sorry? In fact, I have never reached the limit. I have done the test up to 64 millions. I have decided to stop because it makes no sense to go beyond. On this diagram, you have the throughput in terms of virtual thread creation, around 200 per millisecond, with a small decrease starting at 16 million. I have added on each column the size in gigabytes of the Java heap. Because to achieve such result, it is important to properly size the Java heap. Again, with platform threads, the limit on my macOS is 4,000. In terms of memory footprint, it's very linear, from 1 million to 64, about 1 kilobyte per virtual thread. Don't forget that this example is very simple with a very small heap size. It doesn't reflect production. In terms of carrier thread, we have used between 3 and 8 carrier threads. Why 8? Because it is the number of CPU cores on my machine. So this is really impressive. 8 carrier threads, 8 CPU cores to run 64 million virtual threads. I have also decided to play with different garbage collector algorithms. In the context of my test, the best results have been achieved with ZGC. ZGC, which has become generational with Java 21. So, does it mean that ZGC is always better with virtual thread? Clearly, no. But it illustrates that it can be interesting when using virtual thread to test different garbage collector. As a reminder, G1 is the default. Okay. In some situations, the virtual thread cannot be unmounted from its carrier. When calling continuation.yield, the unmount doesn't happen. This is the case when calling synchronized code in block or method. There is a technical limitation currently. Maybe it will change in a more or less time, I don't know. But for the moment, when you execute synchronized code, the carrier thread cannot be unmounted. The same happens when you call native code with GNI or foreign function. Is this a problem? It depends. It can be if the processing is slow, typically doing some I/O, and often called. Otherwise, it may be okay. What do we do in terms of observability and monitoring regarding virtual threads? First, we can track peanut threads. There is an option when you launch the JVM, track peanut threads, and you can have a short or a full description. This is the example of the H2 JDBC driver, and we can see that we have a peanut thread here. By the way, there are plenty of peanut threads in JDBC drivers, generally speaking. It is also possible to track peanut threads using JFR, Java Flight Recorder. There is a peanut event which is emitted with a threshold of 20 milliseconds. And this is very interesting because it enables to spot critical peanut threads. Peanut thread may not be a problem. Peanut threads during more than 20 milliseconds are a problem. There are 3 other GFR events enabling, let's say, to do some statistic on virtual thread lifecycle, start, end, and submit failed. What can we do more in terms of monitoring? We can use a G command to get thread dumps of virtual threads, either in plain text or JSON. JSON proposes a hierarchical representation. It is very, very, very verbose. Plenty of repetitive data. Clearly, it's not possible, it's not easy to spot issues navigating in this kind of thread dumps. Maybe it will be improved in the coming version. Okay? And of course, you can use usual Java tooling to track, to monitor the memory and the garbage collector. In terms of configuration, what can we do? First and foremost, properly size the heap, in particular, the maximum size of the heap. If the garbage collector starts to do plenty of full GC, like in this example, you are in the danger zone. Unlike virtual thread, platform threads, there is no limit when creating virtual thread. You are invited to create as many as you want. Okay? Even if there is not enough memory, the system will try to obey to create virtual threads, and it can come to a situation where your application slows down and even collapse. Because on the one side, your application will create virtual thread, On the other side, the garbage collector will fight to free some memory. So sizing the heap size, and in particular the maximum size, is the very first configuration recommendation. You can also choose the garbage collector. We have seen the influence of garbage collector, so depending on your focus, latency, or throughput, you have different possibilities. And you can also configure the first join pool of carrier threads. Okay? Parallelism by default is equals to the number of CPU core. It means that the number of carrier thread equals the number of CPU core by default. This number can be temporarily increased in certain situations decided by the JVM. So max pool size enables to increase temporarily this pool. The default value is 256. Clearly, except if you are in a very specific situation, I do not recommend to configure that. Okay, you can code as usual, but you are invited to make your code Loom friendly. First, avoid synchronized. Replace it with reentrant block when possible. Reentrant block doesn't prevent the thread to be unmounted. You don't need to pull virtual threads. It is counterproductive to pull them because they are fast to create, to remove. So, but you have no safety guard. And in particular, you may have to protect specific resources using semaphore, typically when you have to manage outgoing connections. Also, use thread locals with care. Thread locals enables to share variables in the context of the threads. They have been designed a long time ago with Java 1.2 with 3 design flows: unbounded lifecycle, unconstrained mutability, and expensive hierarchy. These design flows are acceptable with hundreds of platform threads. They are not with potentially millions of virtual threads. So remove as much as possible thread locals. Thread locals are intended to be replaced by scoped values. Unfortunately, scoped values for the moment have been delivered in preview mode with Java 21. Okay. In reality, we don't have to create virtual thread by ourselves. We can rely on our framework, which does the job. Let's take the example of Quarkus and Helidon. I guess most of you know Quarkus, at least the name. So Quarkus enables to build fast microservices, cloud-native Java application. Okay? By design, Quarkus is reactive. It is based on Netty and Vertex, and it makes a distinction between IO threads and worker threads. IO threads are used for incoming connections. They can run reactive programming, but they must not be blocked. Forbidden, strictly forbidden. If you need to block, you have to use worker threads, typically for imperative programming with Jakarta IE and microprofile. By default, worker threads with Quarkus are platform threads. There is an option which enables to run worker threads on default thread with an annotation. So Quarkus proposes a hybrid approach, an intermediate approach where you can mix in the same application, platform, and virtual threads. It's a good approach to discover virtual thread, to do some tests, to see how it works, and so on. In production, clearly, I do not recommend to mix platform and virtual threads. For me, it's clearly a nightmare to monitor. Helidon. Helidon is less popular than Quarkus. How many of you have heard of Helidon? Okay, a few. So Helidon is very similar to Quarkus in terms of objective. But it has taken an opinionated approach regarding virtual thread adoption. Helidon 3, which is the current stable version, is based on reactive platform threads and a reactive engine web server based on Netty. So no virtual threads at all on Elidon 3. Elidon 4, which is still in development and target Java 21, is virtual thread by design. Netty has been replaced by Nima, which is a brand new web server based on virtual threads. I've decided to do some tests on my macOS, Quarkus, Elidon in different modes, based on a simple REST application backed by a H2 database. And the test consists in injecting 40 incoming transactions with 10,000 requests on each, with 3 endpoints, one that returns immediately, one that do a SQL call, and one that do a SQL update. Quarkus 4 in JVM mode. This is the result. I have observed, on average, an improvement of around 10% in my test. Again, this is a simple performance test. It is not a benchmark. It does not reflect production, but it gives a trend. Cloud native using GraalVM, the difference is less important, around 7%. So you can use virtual thread with GraalVM, but the result is not that impressive. With Elidon, the result is more impressive, around 20% of improvement. Sorry? Good question, sorry. The throughput in terms of requests per second, okay? So about 20% of improvement between Elidon 3 and Elidon 4. Elidon 4 has been totally redesigned on virtual thread, as a reminder. So conclusion, as developer, what should we do? Short term, let's say in the following 6 months, learn virtual threads. Make your code Loom-friendly. Check how your framework and libs adopt virtual threads. The maturity is not the same. The Java ecosystem is moving fast, but not all frameworks and libs are ready. Bench and rebench regularly. Things are improving fast, very fast. Get familiar with monitoring tool. I have explained that navigating in a virtual thread dump is not that easy. Midterm, preparing production. Focus on configuration. First and foremost, heap size. Select the optimal GC algorithm. It's optional, but you can test alternative to G1. You can also configure the for-join pool, the carrier thread for-join pool. If needed, I won't recommend to start by this. By default, it's okay. Check monitoring tool improvement. I expect many improvements in the JVM regarding that. In the long term, you are invited to test structured concurrency and scoped values and do some feedback to the community and replace thread local by scoped values. But in the midterm, because for the moment, these features are only in preview mode. So thank you, that's it for me. I don't know if you have time for questions. Are you totally lost in the threads? It's a rather technical topic. So.
I have a question. I mean, I really like Project Loom, but I ask myself if it's significant in typical business application where the scaling is usually done externally by some cloud system, but my application is rather simple.
Okay. Good question. I think that in the coming months, virtual thread will become the natural way to do with Java. It will be more and more adopted by frameworks and so on. We are at the beginning. We have seen different adoption strategy. And I think there will also be very strong improvement in the JVM. for instance, regarding the way the Java stack is saved and restored from the heap, there are many improvements expected in that area. So you are right, we are in the context where we can ask ourselves the question, do I need to switch to a virtual thread right now? But I guess that within 1 year, virtual threads will be everywhere. So that's why for the following 6 months, I invite you to test, to make your own opinion, to see how to configure things, and to see the benefits.
Thank you for the excellent presentation. What do you think about people that have invested a lot in changing their code to reactive? What do you see the future of reactive being in relationship with Project Loom?
Good question. Reactive programming, in my opinion, still makes sense. In particular, if you have already implemented some very good reactive code, it makes no sense to turn it into virtual thread. Reactive programming makes sense when you want to avoid a memory consumption. Clearly, when you are in a constrained environment, very careful about the memory, virtual reactive programming remain a good option. This is my opinion. You have a question?
Yes, a bit different. In your benchmarking, you say you sent I don't know how many requests. Yes, can you recommend some tools to actually do that, like performance testing? Some performance tools you are using to do that benchmarking.
Yes, you can use clearly tools like Gmeter to define your scenario, to test. These were just performance tests. The database was very small, but because in the end, what is important most of the time is the interaction with the database. If you have a very powerful middleware based on virtual thread, but the relation with the database is very poor, you will still have bad performance. So virtual thread won't improve every situation. We have seen that for in-memory computing, they provide no benefits. And again, you will still have to fight with the usual problem you have with Java applications regarding performance against the database, against the queuing system, and so on. So in terms of tooling, just I would say use the usual tooling for. I think that Gmeter has switched to virtual thread itself to inject inject a process, and then test as close as possible to your production environment. Don't imagine that just switching to virtual thread will provide a miracle. It's interesting, it's powerful, but doesn't prevent from making realistic benchmark and see how it works. And again, prepare you for the following year, I guess.
Operating system does a context switch. It stores all memory registers in the memory, or CPU registers in the memory, floating point things and everything. How does Loom it? Where does it store it, and does it store all registers or only those who are used?
Oh, a very precise question. During context switch, so the main principle of virtual thread is that platform thread and consequently OS thread never block, similar to reactive programming. They are unmounted, but they are not blocked. I have discussed with José Pomar, for instance, who explained that there are very strong improvement expected in the way the Java stack is saved and restored. With it's just a bulk copy. It's a very fine copy, optimized, just copying only what has changed in the stack and restore only what has changed. So I cannot answer precisely your question, but it's an area of improvement for the upcoming Java version. And another area of improvement is, for instance, sticking to new I/O operation with IOU ring and things like that. So the Java ecosystem will clearly evolve regarding that. Okay, thank you very much. Have a good day.